Good evening, Carmarthen. This is Ancient Light. It's a short talk I wrote a few years ago at a particular time when we were all thinking about perhaps other things. It was a lockdown challenge because, as we're all acutely aware, back in 2020, life as we knew it changed. Life in lockdown. So the appearance of this little beastie led to all sorts of things appearing on floors and pavements all over the UK. Keep your distance. Keep 2 meters from everybody else. But instead of looking down at my feet, trying to decide if I was 2 meters away from everybody else, the words of Stephen Hawking resonated. He said, "Remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist." So I thought, well, if we're in lockdown and I can't go visit my friends, instead of thinking about keeping my distance from other people, I wonder just how far is it possible to see? With a camera, what's the most distant object I could possibly catch? This seemed like a reasonable lockdown challenge. So we all know that the universe is vast and the universe is ancient. And we know that large telescopes throughout the world have imaged galaxies that are billions of light years away. But I asked myself, is it possible to capture an image of one of these very remote objects but without using a telescope? I've got a camera, I've got a telephoto lens. Is it possible to capture a very distant object, something as far away as perhaps the other side of the observable universe? Spoiler alert, yes it is, otherwise I wouldn't be giving you this particular presentation. So it started by me trying to find a relevant target. Don't worry about reading this. This is just the front page of a paper that I read. And this paper surveyed a lot of these objects called quasars. What is a quasar? Well, a quasar is the nucleus of a galaxy that emits enough light such that it can be seen at enormous distances of many billions of light years. So I figured if these people have written this paper and have tabulated and surveyed lots of these so-called quasars, is there one that would be a suitable target for me to photograph? We are talking about the summer of 2020. So it had to be an object which is high enough in the sky so that I could see it during July of 2020. So I looked through their list and tried to decide which of these objects would be suitable. I wanted one that was very bright, very remote, otherwise I wouldn't be able to see it if it wasn't bright, and it had to be high in the UK sky. So when we're talking about the nucleus of a galaxy, we don't really know what it looks like because all of these objects are too far away. The best we can hope for is this, an artist's impression of what a quasar might actually look like. We think that at the centre of all large galaxies there is probably a supermassive black hole. In other words, a black hole with a mass far, far greater than the mass of our Sun. Perhaps millions of times greater, perhaps billions of times greater. And these large black holes are energy sources such that in the neighbourhood of the black hole, not from within the black hole itself, as nothing can get out of a black hole, but in the neighbourhood of a black hole, enormous amounts of energy can be released. We don't fully understand the mechanism, but we know that these are very bright objects. So regardless of what they look like, I figured that if I could look through this survey as published and find an object, there should be one that is bright enough to be seen, even though it's very remote, and high enough in the sky to be visible above the UK. And in the end, I found such an object. It goes by the wonderful name of J161737 blah 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 blah. They don't give them nice sensible names. Their name is effectively the coordinate, the right ascension and the declination, the coordinates on the sky. And this is the spectrum that these people took. The spectrum here ranges from blue on the left to red on the right, and the units are angstroms. 1 angstrom is 1/10 of a nanometer. Why is the spectrum important? Well, because the spectrum can be used as a way of gauging the distance to the object. Now, I'm not going to go into spectral analysis, but these people assure me that this feature here, this increase in intensity at a particular wavelength in the red part of the spectrum, if you were to look at a laboratory source, you would expect this particular feature to occur not at 6500 angstroms, but at a much lower wavelength, a much shorter wavelength. So these people reckoned that that peak has been shifted from where it ought to be at 1200 angstroms, and it's been shifted to 6500 angstroms. Why do features in a spectrum get shifted? Well, there's a number of different reasons, but for very distant objects, the features in a spectrum can be shifted because the universe is expanding. So if we think of the wavelength of a particular colour of light, let's say, take something in the middle of the spectrum, green light, that has a particular wavelength, but because the universe is expanding, if an object emits light of a particular wavelength, then that wave gets stretched as it goes from the distant object to us, because the universe is expanding and all objects are separating, or at least all objects on the largest scales. Galaxies are moving away from each other. So they reckon that this particular peak, if we were to look in a laboratory, we would find that particular peak and it would occur at 1200 angstroms, but it's been shifted much longer wavelengths to 6500. And we can quantify that because the convention is, if you know that a particular colour or a particular wavelength has been stretched from the original value when it left the object to a value that you can now measure at the end of your telescope, well, the shift divided by the original value is what we call the redshift. It's a dimensionless quantity. It's the amount it's shifted compared to its original value. And if we think of the difference of 1200 and 6500, the difference is 5300. If we divide that by 1200, we get a redshift of 4.3. So a redshift of 4.3 means that the waves coming from this object have been substantially stretched. Because it is such a remote object, the expansion of the universe has stretched the light from this object by a factor of 4.3. And that is a very big number. That means that this is a very remote object. It is the most remote object I could find in this catalogue that is visible from the United Kingdom. We'll come back to exactly how remote is it, what is the distance to this object. We'll come back to this once I've described how I obtained an image of it. So I know where it is in the sky because its name is effectively its coordinates. So I could look that up in a star atlas and I could tell where I wanted to photograph. What I did was to take my Nikon camera with a telephoto lens. The spec is on the right hand side. It doesn't really matter what type of camera it is. I chose a 300mm lens because that's the lens that I use for other purposes. I put the camera and the telephoto lens onto this white box here called a tracker, a sky tracker or a star tracker. It's basically a motor in a box, and its one function in life is to rotate the camera that's sitting on the box, to rotate it at 1 revolution per day, which is of course the rotation period of the Earth, such that as the Earth rotates and the sky appears to move, this box will move the camera in sync with that, such that the camera will follow the apparently moving stars. Effectively, it's compensating for the rotation of the Earth, and hence I'll be able to get hopefully nice sharp images of this distant object. The camera and the telephoto lens, I've actually used them only a few weeks ago. I used that same combination to take pictures of wildlife. I was on safari a few weeks back in Africa, and I've used exactly the same camera and lens to take pictures of animals. And it's not been modified in any way. Neither the camera nor the lens that I've used, the ones that I've used for wildlife photography, neither of those have been customized or modified in any way for astrophotography. They are just, if you'll excuse the expression, bog standard camera and lens that you would use for taking pictures in daylight. So the question I set myself is, if my camera and lens have been used to photograph, for instance, zebras, is exactly that same photographic setup suitable for taking a picture of a galaxy or the centre of a galaxy, a quasar, at a distance of billions of light years? So I pointed the camera on top of its little tracker. I pointed it in the constellation of Draco because that's where the coordinates told me to point. There's the constellation of Draco the Dragon, for those of you who know your way around the sky. There's the constellation of Ursa Minor, and that on the right-hand side is the pole star, Polaris. The rectangle here shows the field of view. The dot in the middle is not the quasar. The quasar is much too faint to show up on a star map like this. I found that there was actually a 5th magnitude star at the centre of this rectangle that is quite close to the quasar. Just by coincidence, the line of sight to the quasar happens to be close to this particular star, so by pointing my camera at this star, I figured that the quasar ought to be close by, even though I can't see it in the viewfinder of my camera. So Draco is high in the sky during the summer at northern latitudes, and so this is nice and high in the sky. I didn't want an object close to the horizon, which would be more difficult to photograph and would require me to look through more of the Earth's atmosphere. So it's nice and high in the sky, and a star close by allows me to figure out which way I should point the camera. So this is late July 2020. We don't get much night during the middle of the summer. The time from evening twilight to morning twilight is only about 2 or 3 hours. So I tried taking images for as long as I could. In other words, I exposed for about 2 hours or so. I didn't take one long 2-hour exposure. I took lots of short exposures and then added them together in computer software. That's a fairly standard sort of thing to do. It has a number of advantages. If you have a series of many short exposures and some of them are spoilt by a passing satellite or a passing aircraft, you can simply eliminate those and add up all the remaining exposures. Also, during the 2.5 hours or so that I was exposing, some clouds came by. And so again, some of the images I took were spoilt, and so I've thrown those away and added up the remaining images, which added up to about 2 hours of exposure. And that's the image you can see in front of you there. We see the 5th magnitude star right at the centre, and I figured from its coordinates, I can look up the coordinates of that star, and I looked up the coordinates of the quasar, and I figured that the quasar ought to be simply to the top right, somewhere in here, according to my calculation of the coordinates. I thought the quasar ought to be in the centre of that square if I've pointed this in the right direction. You can't really see as it stands. I had to zoom in and magnify that central region in order to see whether or not I had caught this quasar. So let me blow up that square so we can see it more clearly. And there it is, right in the centre of this image. That is the quasar. Very unspectacular, I'm sure you'll agree. The least spectacular image I've ever taken, but amazing in terms of the fact that it is possible at all. So most of the light from this quasar, this nucleus of a very distant galaxy, is focused into just 1 pixel. If I blow that region up just a little bit more so we can see what's going on in that region, let's blow it up again, you can see now the individual pixels of the image. This particular camera of mine was a 20 megapixel image, so 20 million pixels in total, but the light from this quasar has effectively fallen in just a handful of pixels, and most of the light from the quasar is in that one central bright pixel. So what's amazing is not the fact that that's a very interesting picture in its own right, it's the fact that it exists at all. The fact that it is possible to capture light from a very, very remote object. Just as an aside, for those who like the technicalities, we can ask ourselves, what resolution could we expect from a lens and a camera? In other words, what's the smallest object that we could hope to see with this particular combination of lens and camera? Well, any lens or telescope or microscope has a resolution which depends upon the laws of physics. There's a particular phenomena called diffraction which will limit the amount of detail we can see. And I've calculated the so-called diffraction limit of my 300mm f4 lens. f4 simply means the size of the front element is 1/4 of the focal length of 300mm. So in other words, the front element of this telephoto lens was approximately 75mm in diameter. And according to the laws of physics, the diffraction limit would say that the smallest thing we can hope to resolve is 9 microradians, 9 millionths of a radian. And that doesn't mean much to most people, so let me convert it into something which astronomers will recognize: arc seconds. It's about 2 arc seconds. An arc second is 1/60th of an arc minute, and an arc minute is 1/60th of a degree. So for those who like degrees, minutes and seconds, that gives you an idea of the smallest thing that we can hope to see with this particular lens. But in order to obtain an image, we have pixels in the camera, and when we look at how far apart the pixels are in this particular camera, we find that they are approximately 15 microradians, or about 3 arc seconds apart. So roughly speaking, the smallest thing that we can resolve with this lens is roughly speaking 1 pixel in the image. And just to give a little bit of context, if we would imagine the Milky Way galaxy in which we live, if we imagine imaging that at a distance of billions of light years, it would occupy perhaps a couple of pixels or so. That gives you an idea of scale. Returning to that particular image, that's of course a little crop of only a small part of the whole image. But whilst I was there, as well as imaging the quasar, the galaxy right at the centre of this image, which I verified according to its coordinates, I was also interested, as an aside, to see what else we captured in this particular 8 arc minutes by 8 arc minute crop of the image. And I found there were actually 10 galaxies in there. How do we know those objects circled are galaxies? Well, some of them are, you notice, little ellipses. They're not circular, they're slightly American football shape. That one is a little bit stretched, and this one is a little bit stretched. So they're probably not stars, they're galaxies. And I verified this by looking up the coordinates of various galaxies and identified those 10 objects. It's not obvious from the images themselves that those are galaxies, not stars, but that's what I found. So if there are 10 galaxies plus the quasar in that particular crop of the full image, then I've calculated that the full image probably contains about 7,000 galaxies in total. In other words, if I've identified 10 there, and if I simply scale up the area, there's probably 7,000 galaxies in the full image. Roughly speaking, that's the same number of galaxies as in the Hubble deep field, though these galaxies must be rather brighter, and I've covered a much larger area than the Hubble deep field. So let's return to the idea of, okay, we've got a dot in the centre of our image, but how far away is the galaxy that produced that dot? What's the distance to the galaxy? Well, the distance is a little bit tricky to work out. We can imagine that we've got a galaxy there emitting, let's just think of it as a photon of light being emitted by the galaxy, and that's going to travel from the galaxy to Earth. So we can think of the distance from the Earth to the galaxy as meaning the distance when the light was emitted by the galaxy, indicated by that arrow at the bottom. But when the light is on its way, for instance, this little cartoon says when the light is halfway to the Earth, well, the galaxy isn't where it was anymore, because the universe is expanding continuously, And hence, as time goes by, as the light is en route to the Earth, the galaxy will move away from us because of the expanding universe. So halfway between the galaxy and Earth, if the light is en route, the galaxy will be further away, so the distance will have increased. And we can play that game all the way until the light arrives at Earth. And once the light has arrived at Earth, the galaxy is even further away from us. And so you can see that there are nominally 3 different distances which we could define as the distance to the galaxy. Do we mean the distance when the light left the galaxy? Or do we mean the distance that the light has travelled? Or do we mean the distance now that the light has arrived because the galaxy is now further away? And when it comes to determining these distances, we have a problem. Not least because if we think of the middle one, how far has the light travelled? Well, that's actually quite tricky, because when we ask that question, we have to remind ourselves that the light is actually travelling through space, and space is continuing to expand. The galaxy emitted that light long ago, and the galaxy is now doing its own thing. The light hasn't arrived at Earth yet, but the light is travelling through space, and space is expanding. So trying to work out how far the light travels is actually a bit conceptually and mathematically a bit tricky. It's a bit like imagining a swimmer swimming through water at a particular speed, but the water itself is moving. Imagine swimming against the tide. You're trying to swim to the left, but the tide is dragging you back to the right, because you're not moving through static water, you're moving through water which is itself moving. Another analogy you can use for thinking about the light travelling from the galaxy to the Earth is imagining an ant moving along a rubber band. If the rubber band is static, then you can easily calculate how fast the ant is travelling. But what if somebody is stretching the rubber band as the ant is walking? Then trying to work out how far the ant has walked is now tricky. You've got a speed of the ant relative to the rubber band, and the rubber band is stretching, just like space is expanding as the light travels through it. So it's a rather tricky thing to get your head around, and it's a rather tricky thing to calculate, but it can be calculated if we understand how the universe is expanding. Now that relies on a number of different observations. It relies on the expansion rate of the universe, which is quantified by something that we call the Hubble constant. And it also depends on other factors, the details of which I'm not going to go into, and that is what the universe is made of. How much matter is there in the universe? How much so-called dark matter, matter that we don't really understand, and this even more enigmatic dark energy. But if we do have an estimate of what is the Hubble constant, the expansion rate of the universe, and how much matter and energy is there in the universe, then we can calculate how the universe is expanding. And we can use that to show that an expanding universe will stretch light. And remember, that's the one thing that we can actually measure is the redshift. We measure the spectrum of light. This is not something I've done. This is something that other people have done. If we measure the stretching of light, if we understand the expansion of the universe, then we can work out the distances to objects. And that's what I did by throwing the numbers into a spreadsheet to produce these curves. So these 3 distances are the 3 distances that I mentioned on the previous slide or two. How far was the distance from the Earth to the object when the object emitted the light, so-called distance, that was distance then when the light was emitted. How far has the light travelled, the so-called light travel distance, that's the green line. And the top one, the distance now, the red line, is now that the light has arrived and the object is further away, how far is it from us now? So there are these 3 distances. Notice that if the redshift is quite small, if the light hasn't been stretched much, then all of these three lines are effectively the same line. But if the light has been stretched a lot, redshift of 1 or 2 or 3 or 4 or 5, then the red and the green and the blue lines are all very different. So let's think about our quasar, which according to the people who did this survey has a redshift of 4.3. So let's put that in. There's a redshift of 4.3, and so there we can read off the three distances to this object. Let's put in the numbers here. And to avoid any confusion, let me just erase the curves because it's only the redshift of 4.3 that we're interested in for this particular quasar. So let's get rid of the rest of it. And let's remind ourselves what these three distances mean. So if we understand the expansion of the universe correctly, what it means is the image of the quasar that I obtained with my camera, the quasar must have been about 5 billion light years away when the light was emitted that I caught with my camera. 4.6, let's call it 5 billion light years. That's the distance when the light was emitted. But it's taken about 12 billion years for the light to get from that quasar to us. Light travels at 1 light year per year, so it's taken 12 billion years to reach us, so the light travel distance is 12 billion light years, strictly 12.4 billion light years if we've calculated things correctly. Remember that the universe, we believe, is 13.8 billion years old, but that this light has taken 12 billion years to reach us, more than 12 billion years. The light has taken approximately 90% of the age of the universe to actually reach us. The light was emitted long, long, long before the Earth even existed. During those 12 billion years, the universe has continued to expand. So during the 12 billion years that the light was travelling to us, the universe has continued to expand such that the quasar is now approximately 25 billion light years away. An absolutely incredible, mind-numbing distance. But even if we ignore the billions just for the moment and look at the numbers, there's something very interesting that we can deduce from these. The distance has changed from 5 to 25 billion light years, approximately. How long has it taken to do that? It's taken approximately 12 billion years. So it's changed from 5 to 25, so its distance has increased by approximately 20 billion light years, but it's only taken 12 billion years to do that. So it doesn't take too much to figure with a little back of the envelope calculation that during the light travel time of 12 billion years, the distance has increased by more than 12 billion light years. And given that speed is distance over time, we can work out the average speed of this recession of this galaxy, and we find its distance to the galaxy has increased by 20 billion light years in a timescale of 12 billion years, which means on average, during the time it's taken for the light to get here, its recession speed is more than the speed of light. It's about 1.6 times the speed of light. That sounds wrong when you first think about it, but this doesn't go against anything that Einstein has told us. Einstein says that objects cannot move through space faster than the speed of light. But here we're talking about a remote galaxy that's receding from us because of the expansion of the universe. And the universe can expand at any speed it wants to, because we're not talking about a galaxy moving through space. We're talking about space itself that is expanding. And it can, and indeed does, expand faster than the speed of light. Even some closer galaxies are receding from us faster than the speed of light. And this one, on average, has been receding from us on average at about 1.6 times the speed of light. Again, assuming that we have got a correct understanding of how the universe is expanding, we can calculate how its velocity has changed with time. 1.6 times the speed of light is just an average. But we can calculate its actual recession velocity, the velocity at which it's moving away from us, and we find that it was moving away from us at more than twice the speed of light a long time ago. This is time in years. So 0 was the Big Bang, and we are currently here at 13.8 billion years after the Big Bang. So it started receding from us at about 2.2 c. But after initially slowing down, you can see the velocity was decreasing. That's perfectly understandable if we think about the universe expanding. Gravity is pulling on everything, and so you would expect the recession velocity of objects to slow down, simply because gravity is putting the brakes on. So having this red line fall is no surprise. But what is a surprise is that it doesn't keep falling, it bottoms out. And for the last few billion years, this object has actually been accelerating away from us. Indeed, all objects, as far as we can tell, are now accelerating away from each other. Why should that be when gravity should be slowing things down? What is it that's making things fly apart faster and faster and faster? The bottom line is, we don't know. We've given it a name, dark energy, but just because it's got a name doesn't mean we understand what it's doing and why. So this discovery that things aren't just slowing down but they're actually starting to speed up is a discovery that was only made in the last few decades. It's not something we've known about for centuries. We've known about an expanding universe for over 100 years, but the acceleration is a little bit of a mystery. But that's another story. So let's think about what the light is doing, and I've tried to indicate how weird it is from this diagram. This is a chart, if you like, a plot of distance from us in billions of light years. So 0 is where we are, and further to the right are greater distances. And time runs vertically. So the Big Bang was at 0, and we are currently here at 13.8 billion years. So that's us here and now, the little orange dot. And the green dot represents when and where the light left the quasar. The light left the quasar 12.5 billion years ago, which is why the green is down here. And the quasar was 4 and a bit billion light years away from us, so 4.6 billion light years. And you might think that if the light is going to leave that quasar and the light is going to end up coming to us, then presumably the light follows that path, and the light gets closer and closer and closer to us as time goes on and on and on and on. The light gets closer and closer and closer to us until the light arrives here and now. But no, it can't have done that, because the quasar is receding from us at twice the speed of light. And this is where you have a real problem getting your head around what's going on. The light is trying to come to us, but space is expanding faster than light. It's like swimming through water where the water is moving faster than you can swim. So what happens is the light gets dragged backwards. This is really, really weird. So the light doesn't get closer and closer to the Earth as time goes by. 2 billion years after the Big Bang, 3 billion years after the Big Bang, 4 billion years after the Big Bang, the light is actually further away from us as time goes by because it's getting dragged backwards by an expanding universe. Only after a few billion years does the light actually start to make headway and then eventually find its way to us. So the light from the quasar actually follows this weird curve, which is a result of the expanding universe. It's weird to us because we're not used to the idea of things moving and trying to go from A to B whilst the distance from A to B is changing. The distance from Liverpool to Manchester is the same today as it is last week, and it will be the same tomorrow, and it will be the same next year. The distance between 2 points on the Earth doesn't change. Let's forget plate tectonics and things like that. We're not used to the idea of the distance between 2 points changing day by day, such that if we wanted to travel from A to B, we'd have to take into account the fact that the distance keeps changing. We think of 2 points on the map as being fixed, and therefore if I want to go from A to B, I can just go at a certain speed and I know when I'm going to get there. Doesn't work that way with the universe. So if that's what the light was doing, initially getting further away and eventually making it to us, what was the quasar itself doing? Well, the quasar is simply being carried along by the expanding universe. So the distance from the quasar to us simply gets larger and larger and larger and larger as time goes by. That's indicated by the red dotted line. I've dotted it simply because, strictly speaking, it's not a straight line. If you remember, I've said that the velocity of this object is changing. It was going fast, then it slowed down, now it's going fast again. And so, if you think of this particular line, this would indicate its speed is constant if it's a straight line, but in fact it's going faster and slower, so it should be a slightly wiggly line, and I didn't really want to draw a wiggly line, so I've simply drawn it as an artist's impression of where the quasar is heading. It's heading off to the right, such that by the time we get to the now point of 13.8 billion years, the quasar is some 25 billion light years from us. I like to think of it from the perspective not of the photographer on Earth taking the picture, but think of it in terms of the perspective of the light itself. The light was emitted by this quasar shortly after the Big Bang, 1.4 billion years after the Big Bang. Remember, the Big Bang happened some 13.8 billion years ago. The light had already been travelling for some 8 billion years before the Sun and the Earth were born. It continued on its journey for another 4.5 billion years. Life evolved on Earth. The light travelled on. Dinosaurs came and went. The light travelled on. In the last million years of its journey, the light arrived at the edge of our Milky Way galaxy. It crossed a few spiral arms of our galaxy and it entered the solar system. In the last few hours, it finally arrived at Earth, travelled through the atmosphere in just a fraction of a second. It hurtled towards England, dodged a few clouds, and entered the lens and hit the camera sensor. And you've seen the result. Just a pixel in the image. But what a journey. So here's a graphical summary of what I've been talking about. I've taken the camera and lens that I use for normal daylight photography. I put it on a little box called a star tracker to compensate for the rotation of the Earth. And then on a summer's day in 2020, correction, a summer's night, I pointed it towards that particular star in the constellation of Draco that I knew was quite close to the quasar. And then by blowing up a small section next to that star, I found that I had indeed caught the light from this very distant quasar. A quasar that is some 25 billion light years away, and the light that produced that dot took more than 12 billion years to reach the camera. So yes, it is possible using a normal camera and lens to catch what I would like to think of as a quasar's ancient light. Thank you very much for listening.